strange to be cancelled if nobody told me. Okay, we'll have a look at errors now. Oh, sorry. So I need to define some terms that you'll need in your report. When it opens, it's stuck. Right. Oh, here we go. Okay. So can you write these names down? Oops. Okay. Right, you got that? Yes? Okay. So, I'll tell you what you need to write down, so just a couple of things to cover first. When you calculate something in physics, it's very, very important that with your calculation you have a measurement of how uncertain you are about your result. Okay, so if your result doesn't have this, it's not really a worthwhile result. So whenever you make a prediction or a value or a measurement or a calculation in physics, you must always include the uncertainty. So for it to have any meaning, it cannot just be the value by itself. You have to say how precise you were. So we'll need to look at some terms for describing that. So I suppose you could say that you're looking at two key things. A numerical value, which is the best guess of what you're measuring, and number two, how uncertain you are about that measurement. So the idea is, with everything in physics, number one, you have a measurement, and then number two, you have an uncertainty with the measurement. Do you know what I mean when I say uncertainty? Yeah. So we can have more precise definitions now in a moment. So you can never know the true value. If you think about it in physics, you can never know the true value, because whenever you measure something, it won't be perfect. And you probably talked about this in chemistry, maybe? A little bit, kind of. So you can never know the true value. So in practice, we use an accepted reference value, which is what you would call in chemistry, I think Lorraine calls it the literature value. Yeah. So you can never know the true value, but we do have literature values. The accepted reference value is usually established by repeatedly measuring. This value is not the reference value that is found published in a reference book. Such reference values are not the right answers. They are measurements that have errors associated with them and may not be totally representative. So, what's to say about here? I don't think there's too much here that you would need for your report. Just to say that, of course, there's not really a right answer. It's not like a maths problem.
So I have to say something like this?
No, not yet. This is just giving you a bit of background. Why have I got this twice? I need to delete that. Right, so this is the first definition that you definitely need to know. So you might want to write this down as it is.
So I sent the email to Roland saying I would like to discuss my coursework one day.
Did you say please in it?
Please.
Better. Right. Accuracy is the closeness between the measured value and the true value. So, if this is the true value and this is what you measure, the accuracy is how close you are to the true value. Do you have the same vocabulary in chemistry lab work? Not accuracy, no? Okay. Well, you clear what accuracy means? Yep. The next word is error. Error is the difference between a measurement and the true value of the measurement. Error does not include mistakes. So you might say, how is this different from the previous definition? So just focus carefully. Previously we had accuracy. That's the difference. If you go back here. That's the difference between the measured value and the true value. But for error, that's the difference between the measured value and the true value of the measurement. So it's like when you measure something, you won't measure it perfectly. There's an error in the measurement. That's different to the measured value and the true value. So this number here, this error should be really, really small because it's a problem maybe of the measuring machine. Yeah. Error does not include mistakes. So if you measure incorrectly, you hold the meter stick upside down, that doesn't count as an error. That's kind of called a human error, I guess. Do you do this word in chemistry?
Yeah.
Human error? Values that result from reading the wrong value or making some other mistake should be explained. So who was it that had the weird point on their graph? Was it you or?
The last experiment?
Yeah.
I had a
It was you. Oh, it was you. So I said, if you keep it, you have to explain it. Yeah. And you could exclude it if you want. Error is what causes values to differ when the measurement is repeated. So if you think about it, if you measure something and you measure it again, you should get the same value if it doesn't change, right? But because of error, you'll get a small, different value. And none of the results are preferred, meaning if you do the measurement 10 times, they're all slightly different. It's not like one of them is better than the other 9. They're all the same. It's not possible to completely eliminate error. That is not possible. You cannot do that. But you can control it. And often a lot of effort goes into calculating the error. It's important to know how wrong your answer could be before you can, ask people to use it. So there's a lot here, but the most important thing is you understand what the word means, error. Okay, so if we think about, for example, the Snell's law, the first experiment, what was the cause of the error? Or what was the error? It was the movement, yeah. And you had the same thing happening with the multimeter and the ammeter as well. The voltmeter and the ammeter. And also with the time for the pendulum, I said to do it twice, but you never. Well, okay. So I think somebody got exactly the same time twice. You shouldn't get the same. Usually, don't get the same time twice. So this is error. Systematic error. Have you heard of this one in chemistry? Yes. Yeah, so what's systematic error?
Equipment.
Usually equipment error, but what type of form does the error take? How does it affect the measurements? Because it usually affects it in a very particular way. No? Systematic errors usually make all the results, all the measurements off by the same amount. So, like for example, if you have the meter stick, but the bottom is missing, like the bottom first centimeter is missing, then it means all your lengths will be off by 1 centimeter. So this is a systematic error. There's of course a number of measurements that the mean value is, it means that the value is constantly displaced. That's what I'm trying to say, that everything is off by the same amount. And it's usually, like you said, because of the equipment. So it's quite predictable error. If you know about this error, then you can easily fix it by just adding 1 centimetre to all the measurements. The causes may be known or unknown, but you should, if you see this in your data, you should correct for it. Now, none of you should have this in your data because nobody really used the equipment the wrong way. The only example I can think of is with the meter stick, and maybe
Small ruler.
yeah, maybe with the ruler. The meter stick and the ruler would be the two. No instrument can be calibrated perfectly. So when a group of measurements systematically differ from the value of a standard reference specimen, an adjustment in the value should be made. So there's a lot going on here, but again, I'm just making the point that you cannot calibrate it perfectly. You know this word, calibrate?
Reset.
Reset, yes. You can't reset the measurement equipment perfectly. So maybe your meter stick will always have a tiny error, like maybe it's like 0.1 millimeter too long. You know, maybe just because it's stretched out a little bit over time. You know, like meter stick, we think about it not changing its length, but you know, if it's warm, maybe it expanded a little. You know, so you can never have it perfect. Systematic error can be corrected, but only when you know the true value. Okay. Random error. So that's another type of error. Does anyone know random error? I don't know.
Like if two people have like different opinion, for example, in terms of she said like, well, the point, like someone could say 0, someone would say no, it's not 0.
Is that random error or is that different type? Are you talking about reading the machine?
Yes.
Not quite. That's I thought Lorraine had a different name for that, like parallax or measurement error or human. I can't remember. For me, random error is an unpredictable error. It's the type of error that you see in the multimeter, voltmeter. It's just that kind of noise that it's just slightly changing. This is a random error, and you don't know if it's going to go up, if it's going to go down. It's just moving up and down, like with the light and the water. So that's a random error. It's definitely not possible to correct for random error because you don't know what it's going to do. Trueness and bias. So trueness is the closeness of agreement between the average value and the accepted true value, that should say. So you know in chemistry, you probably have to do the experiment many times and take an average. Yeah? And then the trueness is how close your average is to the literature value. This is the trueness then. It's very similar to accuracy. But the trueness applies to an average. Now, when you think about your experiment, you don't take an average, but you do something that's like taking an average in your calculations. I wonder if you can picture what that is. So you don't, when you're calculating the G from the gravity experiment, you don't average anything. How do you get the G? Using the slope. So using the slope is like taking an average because you're using all the values to make one value. Do you get what I'm saying? Like, it has the same effect of taking your data, producing one value, and getting a calculation from that one value. So, trueness is what you would use when you compare your value of G with the literature value of G, for example. Or, when you compare the mass of your system with the true mass of the system when you measure it with the spring balance. Okay, so this is the trueness. Bias is the difference between the average value and the true value. So bias is how different your average value is to the true value. So for example, if you got the mass of the system as 1.1 kilograms, but it was only 1 kilogram when you measured it, then you say the bias is 0.1 then. Okay. Bias is equivalent to systematic error, and a correction to negate systematic error can be made. Although none of you can correct systematic error, because none of your equipment should have a systematic error, because I didn't see anybody using anything incorrectly. So you although your answer might be slightly off, you can't do anything to fix it, which is fine. Precision. Have you done this one in chemistry? Precision. No, this is a new one? Precise?
Yeah, we know.
You would know the word, you heard of it, yeah. Precision is the closeness of agreement between measurements under the same condition.
Yeah.
You know this one?
Yeah, we did it in chemistry.
See, that's what I thought, yeah. It is a measure of how well a measurement can be made. The number of divisions on the scale generally affects the measurements, and therefore the precision. So like for example, with the meter stick, the smallest value is 1 millimeter. So this is like the precision. What's the smallest value on the photo gates? It was like 0.01, 0.01 I think, meters per second. So this is the precision. You can't measure more accurately than this, more precisely than this. It's the smallest you can measure. We don't talk about bias or error with precision. That's a different thing. Okay. Uncertainty. So uncertainty is, I suppose you could say it's like you saying how wrong you could be. Now, the problem with this is there's so much vocabulary which in general English will be synonyms. You know, if somebody says error or accuracy or precision or uncertainty in general English, it kind of all means the same thing. But in physics and in chemistry, each word has a precise meaning. So uncertainty is basically like you saying how wrong my estimate could be. You know, I think G is 9.8 plus or minus 0.2. You know, that's like the uncertainty. And the uncertainty should include all the errors and all the possible effects and all the things that could have went wrong, both systematic and random. And it's the most appropriate way to express accuracy. So like I said, this is the key one here, which you want in all your physics reports ever, for the end, from now until the end of time. You always have to give an uncertainty with your measurement. So we'll need to have a look at how to calculate uncertainty, which you've seen a little bit with Lorraine, I think. Yeah? Yeah. Okay. Can I close this now? I mean, I'll keep the video recording, but we'll have a look at now how to do some calculations. So they were just lots and lots of definition of terms. But let's have a look here. I'll open up Excel to give you an idea. So have you done the square root formula with Lorraine, yeah? Okay. And then I need to talk about what you need to do for your coursework too. Okay, so did you do any practice questions using the formula? Yeah, so you've used the formula at least once then. Okay. What symbol do you use in chemistry for uncertainty? Or what letter? Or well, how did you write down uncertainty? Joe, you? Yeah, no, but I mean, how did you write it down in your answer? You didn't just say uncertainty is, or did you? Did you use a symbol, a letter? I didn't calculate uncertainty. Calculate the error. Okay. Let's have a look at a little example here. You don't need to type this down, I just want to give you an example. So, let's say I'm measuring the length of something in meters. And it's the same length each time, but it's going to be a little bit different. So like maybe the first time I measured it's 0.88, and then next time I measured it's 0.89, and then maybe it's 0.88 again, and 0.89, and 0.89, and 0.88. So this is my data, for example. So what would be my best estimate for the length of this, whatever it is?
0.885.
Ah, yeah, but how? What do I do to get this? Okay, well, let me put in 0.9 then. Okay, now what? What's my best estimate for the length here? If I have all this data, what should I do? Get the average, yeah. So the average here, 0.887, let's say. Is it right to say that the true value is 0.887? No. But this is our best estimate for what the true value is. We think it's about 0.887. But we know it's not exactly 0.887. That would be foolish because we can see that we're getting slightly different values each time, so we're not certain what the true value is. So this we use as the average, and you can write it like this with these brackets. Around the letter, that means average, or you can put the bar on the top. I don't know what you've done in high school for average. Do you know what I mean? You can write it like this. That means average of L, or you can put the bar on the top. That means average of L. Is this a new symbol for you? Yeah, okay, so you might want to write that down. It's easier to type, which one?
Second one.
Yeah.
That one. Yes. This one, Adnan. Peace out. Oops. Okay. No, that's not what I want, sorry. What was I doing next? Oh yeah. So now we need to calculate the uncertainty. So there's a couple of ways to do it. I wonder, have you seen a way to calculate in chemistry? How to calculate the uncertainty here? Just the error, yeah. And what formula did you use for the error? Yeah, is it like a squared over a, or
A squared over
a squared over
D.
d, b plus
6 squared over D squared.
that doesn't quite sound right, but something like that anyway. Okay, so there are actually, just before I start, there are actually many ways to calculate the uncertainty here, and most of the time they give you roughly the same answer anyways. So let me show you the different ways to calculate it. So if you have a list of data, I'll just call it x1, x2, x3, xn, and we want to calculate the uncertainty, and the symbol I use is delta x, or sometimes people might use ux like this, depending on which book you're looking at. I think delta x is a little nicer. What you can do is you can take the maximum x minus the smallest x divided by 2. Now that's the easiest way to calculate it. So if I was to use that one, delta x, what's the biggest value here? 0.89 or 9, and the smallest one? 88 divided by 2. So that's my first one. I could say it's 0.887 plus or minus 0.01. This is the
uncertainty.
yeah. Sorry, not delta x, I should say delta L. Now wait, that's only one way to calculate it. That's like the quickest, easiest, and worst way. But they're actually all pretty similar. Okay? So let's have a look at another formula to calculate it from a set of data. The other way to calculate it, roughly, all over n, and it's the difference between the data and the average difference between them. So for example, here it would be the data minus the average. Data minus average, data minus average, data minus average. You keep doing that, and then at the very end, you take the average of those averages, those differences. That's way too small. I think something wrong there. Hang on. No, it's not that small. Oh, sorry. I know what my mistake is. Do you know what this symbol means with the vertical lines?
All numbers come out positive.
Well put. All numbers come out positive. So I just need to change these into positives. And then get the average. Now, it's different, but not hugely different. 0.01 versus 0.006. It's different by 0.004. The other way to calculate it is using this formula, which maybe some of you recognize from high school. Do you recognize this from high school? It's called standard deviation. No?
What is the end?
How many data points you have? Number of data points.
But you didn't divide by.
Here?
Yeah.
Oh, I did. The formula did it for me in Excel. I did. Musharif, if you add these up and divide by 6, you get the same answer. Okay, so let's have a look at what this one gives us.
And is the number of data?
Yeah. Okay, so this one here, we have to look at the difference squared. So we square all the differences, and then after we square, we add them up. Then after we add them up, we divide by 6, and then after we divide by 6, we square root. So let me write that here. We'll add them up. Divide by 1, 2, 3, 4, 5. Oh, sorry, 7. Is it 1, 2, 3, 4, 5, 6, 7, and then also I need to square root. Now, they're hardly different, those two. 0.0061, 0.0069. Okay. These are the three formulas you have to calculate them. So this is the one I expect students to use. This one here is too easy. And not that this one's too hard, but it's a bit of a pain. Yeah, this one here is nice. It's not too easy, it's not too hard, and it's very close to the most accurate one, and better than the least accurate one. You know, so this is kind of a good balance between all the options you have. So this is the formula you should use to calculate the uncertainty. Now, if you think about it, when you did the pendulum, how many measurements do you have for each one? 2. So actually, for the pendulum one, you could only use this as an example. For Snell's law, and for Snell's law, you have to estimate the uncertainty by how much it's shaken. And for the voltmeter, do you remember you should have written down V min and V max? So the uncertainty is V max minus V min over 2, which is actually you using this formula without realizing it. Yes? Huh? This one. Isn't it like V max minus V min over 2? Yeah.
Can you do the second one more time?
Oh yeah, no, I'm definitely going to do more of this now. What we'll do shortly is this, but for newtons. Now, this is the formula for uncertainty, but it gets a little bit more complicated when you're looking at the graph. So, let's say we have x, let's say we have y, and let's say we have our data like this. Now, we have our x data. Here it is here. 1, 2, 3, 4, 5. So if we know our x, we could know what our uncertainty of x is, because we could use this formula to calculate it. And likewise, we could look at our y values, and we could use the same formula and calculate the uncertainty of the y. But what we can't do yet is calculate the uncertainty of the slope. Because when you think about it, this slope could change. If, for example, if this point was to move like a little bit down to like here, then this line would move a little bit further down. So there is an uncertainty with the slope. Now, why would you care to know what this is? It's usually something that you want, that you're interested in. So, for example, let's say that the mass equals 1 over m. If you want to know how uncertain you are about the mass, you need to know how uncertain you are about the m. And that's what we need to look at how to calculate next. Just before we do that, how to combine uncertainty. So, for example, suppose you have some very simple formula. Z equals x times, oh no, I got a better one. Area equals x times y. So you're measuring a piece of paper, and you measure the x many times, and you measure the y many times. What's the best value to use for the area? Well, you should use your average x. You should use your average x multiplied by your average y. That makes sense, doesn't it? But now the big question is, if I know the uncertainty for x and the uncertainty for y, how uncertain am I about the area? So what do you think the formula is that combines these two together? No, it's not. It's not. It's not quite like that. It's like this. So if you want to know the uncertainty of A, it's not this uncertainty multiplied by this. And that's important enough for me to say 2 more times. The uncertainty of A is not the uncertainty of x times the uncertainty of y. The uncertainty of x times the uncertainty of y is not the uncertainty of A. It doesn't combine as simply as that. We have this formula to combine it. The uncertainty of A divided by the average value of A, which you can get from here, is equal to square root the uncertainty of x over the average value of x squared plus the uncertainty of y over the average value of y squared. And you're thinking, wait a second, I think I've seen something like this before, right?
No.
Chemistry? Oh, come on, you must have seen this in chemistry.
Yeah, it's the one we did.
Yeah, that's the one you did in chemistry, yeah. Which experiment did you use it for? So what was the formula? That had, like, what's the X and the Y? What are the two things you're measuring? Okay, what letters do I use? V and C. And how do they combine in the formula? Do you multiply them, divide them? What do you do?
Yeah, and the original formula?
Mhm.
Yeah, n equals CV, yeah.
It's a multiplication.
Yeah.
So N, is it? So N equals V multiplied by C. So you can calculate the uncertainty here and the uncertainty here, and Lorraine probably wants to know the uncertainty of N. You can get it from this formula. Now I'm curious, how did she get the uncertainty of V? Because there's other ways to do it as well. So do you remember how you did that in chemistry?
We did it the first way, yeah. Plus or minus 0.01 or something.
Yeah, but like,
Square root.
are you sure?
Yeah, certainly with the error.
The uncertainty.
Yeah.
You sure? Square root?
Yeah.
Which of the three formulas?
Square root point 1 square plus 1 square.
Yeah.
The smallest plus the biggest? Or?
The same one. Point 1 square plus point 1 square over 2.
Why 0.1 squared?
That is
Plus
the
one
short.
is plus minus
Yeah, that's the error. Or the average.
Let's see. Yeah, so my question is, okay, but my question is, where did the 0.1 come from?
That is short value.
It's systematic error. It's on the whatever.
No, not systematic error, because then it's not plus and or minus, it's a random error. Yeah, where did this come from? Because there is another way to do it, which is even easier than the easiest way, which I'll just write it up here. Uncertainty is half the smallest reading possible on the machine. So you've got 4 ways to calculate uncertainty now. I definitely don't like this one, because this one does not use any data. It comes from the machine. So this will be the least accurate of the 4 formulas. This one is pretty good but too easy, and this one is a good balance of everything. Do you think that's how you got the 0.1 in that plus or minus 0.1?
Point 1 is the value that the last where it will last.
Yeah. So I want to know, where did this 0.1 come from? Is it from the machine? If you were told it in the lab, did something on the machine say?
Plus or minus 0.1.
Fine. So then it came. So then the easiest of all the ways to calculate it is to use the value the machine tells you is the uncertainty, which is printed on it. That none of the physics equipment has that value printed on it, the uncertainty. This only comes about with really expensive machines, I think. What machine was it that you were using?
No, is it?
Pure hit.
Pipette?
Pure hit.
What the heck is that?
Physically, I have plastic and have a pipe. When you open the pipe.
Ah, okay. Alright, well, you could use whatever is printed.
Yeah.
No, I can picture now, there's probably a little sticker on it that says plus or minus 0.1.
And there was plus or minus 0.03.
That's fine then, that's fine, yeah. In the physics lab, they expect you to calculate the uncertainty from the data, and this would be the usual situation for university as well. So as I was saying, you've seen this formula, how to combine the uncertainty. We don't really need this one for your type lab. what you need to learn is, if I have an X and I have a Y and I make a graph and I make a line, how uncertain am I about the slope? You know, so like you could say the slope is 1 plus or minus 0.1. We want to learn today how to calculate that, and that's what we're going to do. You all look exhausted. It's because you stayed up late finishing chemistry. I can stop the recording if that makes you feel better, if you want to fess up to it. Don't worry, trust me. When Lorraine looks at your sleepy heads, she'll know that you stayed up.
She doesn't need it.
So then she won't even. She might think you just naturally look this tired. Yeah. Was it a late night?
No, I woke up early.
Oh, an early start. Yes, okay. So the next part is now using Excel to calculate this, because there's a lot of steps to do it. So before I start, I think I should give you 5 minutes to like get a coffee if you wanted or something, because I'm looking at you and you all look like
10 minutes to sleep.
10 minutes.
Sleep and then wake up.
Are you going to get coffee or something?
Yeah.
Yeah, because I need you. The reason is there's lots of steps about to come up, so I need you fully alert for it.
No, we'll go by lift.
What?
We'll go by lift.
I think the walk might help wake you up.
You want to have coffee?
I'm going to make some coffee.
Where is the...
Are you staying here?
Phone, no more phone.
Oh, that's it. She said, I can't stand Mira anymore. I'm out here.
I swear at the end of the semester, no one will be.
No. I've never lost a class yet. You'll all be there. Well, okay, I won't say you all make it to the end. Some of you will be. I can't expect anyone else dropping out at this point, right?
No, now whatever happened.
Except maybe you could have some incident with your wisdom tea and then you have to go.
No,
And it would just be left with 3.
Because physics is lovely.
Is it? You could have fooled me from your test results.
Connell called me for that.
And I don't have it yet. I know where it is though, so I can have a look at it. Oh yes. Yeah. I'll have a look at the maths exam. I haven't even looked at your coursework. What I mean to say is, Roland double marked it, and then I saw the results. But the maths exam I'll have a look over again. Yeah, the reason things get double marked is so that there's no mistakes. So like when I was looking at your physics paper, as I was going through it, I'm like, oh that's, I never added these 5 points into the final score of one of the section A questions. So that's good news. That puts you. What were you at? Yeah, okay, so that gets you, and your university requirement is a B, isn't it? Oh, well, you've got a bit of slack then, yeah, you don't have to stress too much.
Today, one of them said that you just need to pass for anyway. They showed me the grades.
They've changed it then?
Yeah.
But you don't know if he's doing the same course as you.
He's in the same year and I'm doing civil, so it's more for me.
That's unfortunate to hear because his result was higher than yours.
It's unfortunate.
It's very unfortunate, Mayor.
Look who's back.
Who's back? What happened? What are you doing back here? We thought we'd never see you again. We're taking a coffee break.
Yeah, now you are going
Yeah. Don't lock us out because I'm leaving my key here, okay?
Yeah.
Where is it? No, now you are not.
You can stay there. Don't you have class now?
I also have in this class.
Yeah, like in 1 hour.
Yeah.
You can stay here if you want to. What? Where's the rest of the students? So what are you doing here?
I miss my teacher.
Who, me? But you have me at 3 o'clock.
No, it's new teacher.
For what?
Physics is new teacher.
Physics a new teacher? Who?
Steven what? Yeah, it's new teacher.
Yeah. Do you know anything about him?
No, do you know about him?
I heard he's brilliant.
Really?
It's really good. Really good. You should be
Better
happy.
than you?
Oh, much better. Much
Wow.
better than me. Yes.
That's why a lot of students.
A lot of students are in this class because of it.
Yeah.
That's true. Yeah.
More than in this class.
Yeah, because of me. Yes.
Steven, I done my lab report.
Good. You'll have to do it again.
No.
What?
I thought the lab report is same.
It is, but you have to do it again.
Yeah, but it's better in second half. So
Yeah.
in this half, I done.
I'll check it in a minute. In a minute.
I'm so tired.
Oh, this is still recording. I better stop it, so.